Okay, so let's go ahead and get started. Today I'm going to go over section 9.3, which is on hypothesis testing for two population means where you have matched pairs, which is also called dependent samples. So let's start with this example from 9.3. This is number 3 in the homework. It says a popular theory is that presidential candidates have an advantage if they are taller than their main opponents. And then listed below are heights in centimeters of randomly selected presidents along with the heights of their main opponents. And if you read further, there's a part A and a part B. Part A says use the sample data with a 0.01 significance level to test the claim that for population of heights for presidents and their main opponents, the differences have a mean greater than 0 centimeters. Okay, so let me kind of go over some preliminary stuff and then we'll actually work out this problem. But there's a couple of things we need to talk about here. Initially, what you've got here is you've got two populations. That's why it's in chapter 2. Chapter 2 is all about hypothesis testing for two different populations. Uh, First population is the height of um, presidents, and then population 2 would be the height of their opponent. Now, these are not independent samples of each other; they're matched pairs. So, during a particular presidential election, there'll be the eventual winner will be the president, and that'll be their height, and then their opponent, their main opponent, height would be over here, and so they're matched together because they were both in the same election period. So this is like population 1, population 2. So these are not independent samples of each other like it was in the previous section. And so we have to approach it differently than we did in the previous section. If they were independent of each other, then we would do it just like we did in 9.2. So that's one thing to sort of catch here is that we're working with matched pairs, right? Every time there's an election, there's an eventual president that's elected and their main opponent. And then those two heights are matched pairs. And so population 1 consists of all the heights of the presidents, and population 2 consists of all the heights of their opponents, but they're matched together according to which election they were in. Okay, so that's what's different about 9.3. We're working with claims about two population means, but they're matched pairs now instead of independent samples like they were in the previous section. Now, just take note of a couple things here. If I were to average up all the heights of population 1, that would be, we label that mu sub 1, right, for the population mean. And this would be the average height of all presidents. And then if you average up all the heights of their opponents, that's, mu 2, the population mean for this population, right? Um, so the average height of the presidential opponents, right? And this is a population mean, right? This consists of every opponent. Now, ultimately, what we're going to do is we're going to convert this into actually just one population. So even though we start off with two populations here, we're going to sort of convert it into one population, and it's known as the population of differences. So what we're going to do is we're going to take whatever the president's height is minus their opponent's height. So we're going to take this number here minus this number here. And then that's going to be called D for difference. We're going to label that with a D. And we're going to do this for every single, presidential election. In other words, the entire population, right, of matched pairs. And if we list all those D values, then that's called the population of differences. In other words, go look at every single election, find out the height of the president, find out the height of their main opponent, take the difference between those two. So, this number minus this number, and then you'll get a difference in the two numbers, right? That's the difference for that election. Do that for every election and list all the differences that you get. When you list all the differences for the entire population, that's called the population of differences. It's called, they're called D values. Very similar to X values, but they're called D values because they stand for the difference and the two numbers here. And then if you were to average up these numbers here, this is the mean of the differences. So we label that as mu sub d, right? It's the mean of this population of differences. Okay, so we label it as mu sub d for the mean of the population differences, or the mean of the population mean of the differences that you get from here. Okay, so that's kind of how this is set up. And so then when you take what happened is someone randomly sampled um, a certain number of elections. Let me just see how many. 1, 2, 3, 4, 5, 6. So they randomly picked 6 elections, right? So if you go look at what we've done here, randomly picked 6 of these elections, right? Just at random. And so they end up with 6 of these matched pairs, 1, 2, 3, 4, 5, 6. And then listed the president's height and their opponent's height in each of the 6 elections that they selected at random, and that's our sample data. So this is our sample data. And we're going to use this to test the claim. In this case, they're claiming, if you read this carefully, the claim is that it says test the claim that for the population of heights for presidents and their main opponents, the differences have a mean greater than 0. So they're claiming that if you were to find the difference in the uh, president's height minus their opponent's height in every election, so the entire population, if you found the difference in every one of those matched pairs, they're claiming that this mean here, the mean of these differences here, would be bigger than 0. So they're claiming that this is greater than 0, which kind of indicates that the president is taller than their opponent. In other words, they're probably thinking the taller candidate usually wins the presidential election. That's the claim, okay? So let's go ahead and work through that, and I'll show you how to work it out. Okay, so I'm going to do the traditional method first. We always do. And if you look at the problem, they say want you to test this at a significance level of 0.01. So alpha is 0.01. Okay, and of course, we've done this several times. First thing you really want to do when you run one of these hypothesis tests is to write down the claim mathematically. So let's just go see what that is. Claim again is that the differences have a mean greater than 0. And they're talking about the population of differences for all presidential elections. So again, they're claiming that if you average up these differences here between the matched pairs for every matched pair, right, every single election, they're claiming that the average of these differences will be greater than 0. So the claim is that mu sub d is greater than 0. Okay, so there's our claim. Now this does not have an equal sign in it, so it's the alternative hypothesis. And then of course the null hypothesis would be mu sub d is less than or equal to 0, which we just think of as mu sub d is equal to 0. Okay, so that's how you would set it up. Now, you do the traditional method, you of course find the critical values first, which are the boundaries that we use to determine whether we reject null hypothesis or fail to reject it. So a couple of things I want to mention before we actually do that. We do need we do need to a bell-shaped distribution here. So what's going to happen is when you look at your sample data, we're going to end up with um, what we're going to do in our sample data is we're going to take the difference again between the president's height and their opponent's height, find the difference in those just from the sample data. So here we've got 6 different presidential elections. We're of course going to find the difference between these two numbers again, just like we did in the population. So even though we have matched pairs, we're going to reduce this to sort of 6 numbers, which is the 6 numbers are the difference between the president's height and their opponent. So you'd say 182 minus 67. So the difference here would be 15. And you do this for every one of them, right? 184 minus 179 would give you 5. Sometimes you'll get negative numbers. 173 minus 180 is negative 7. And that's just because the president was actually shorter than their opponent. And 192 minus 76 is like 16, I guess. And then 193 minus 193 would be 0. And then 169 minus 175 would be a negative 6. So you're going to have 6 numbers here, which are the differences between the president's height and their opponent's height. And then we're going to average up those numbers, and we're going to call that D bar. Now, why are we calling it D bar? Because when you put a bar on top of it, it stands for the average. So we're finding, just like X bar was the sample mean, the average of the X values in your sample. D bar would be the average difference for the matched pairs in your sample. Okay. We need the D bar values to be bell-shaped in order for this to work. So you may remember it's no different than trying to get the X bar values to be bell-shaped. And from the central limit theorem, there's 2 ways for this to happen. You either have to have a sample greater than 30. If you remember, the central limit theorem said that if you're sampling more than 30, then the X bar values, in this case, we're just labeling them as D bar values, but they're same. It's the same idea. The D bar values would be bell-shaped if you're sampling more than 30. But the other possibility is that your original population is normally distributed. And when we say the original population, we're talking about the original D values from here, which we used to call X values. But in this particular case, we're calling them D values. So the differences between all the matched pairs for the entire population. If you put that into a histogram and that looks bell-shaped, then the D bar values will automatically look bell-shaped. So we do need one of these 2 facts to be true in order to get the bar values to be bell-shaped. So look, if you look at the particular problem that we're working with, our sample size is actually 6. 1, 2, 3, 4, 5, 6. There are 6 matched pairs. So it's not because n is above 30. And unfortunately, in this problem, they don't say that the population of differences is normally distributed. They don't mention that. So I think that's something we have to assume in order for this to work. So I'm going to go ahead and assume that. They didn't mention it. They probably should have. But the assumption that we're making is that these are, you put these into a histogram, that you get a bell-shaped distribution. So this is the assumption that these are bell-shaped. Okay. And so assuming that this ends up being bell-shaped, right? You take all these D values and you put them into a histogram and it looks bell-shaped. Assuming that's the case, then the D bar values will be bell-shaped because of this second condition from the central limit theorem. It's not because n is above 30 because we're only sampling 6, right? So it must be the case that these are bell-shaped here, which gets us the bell shape here. And so what we're going to end up doing is we're going to take the D bar values and we're going to convert them into t-scores. Now you'd like to convert them into z-scores. Convert them into z-scores, you would say D bar value that you're converting into a z-score would be D bar minus the mean of the D bar values divided by the standard deviation of the d-bar values, the population standard deviation of the d-bar values. By the way, I mean, a z-score, you may get lost in the symbolism here. But remember, a z-score for an x value is z minus, I'm sorry, the z-score for an x value is, remember, x is a random variable. So what do? You take you say x minus the mean of the random variable. You could label that mu sub x if you wanted to, and then standard deviation of the random variable, sigma sub x. We left the x off when we did this the first time, but think of it like that. And now if this is x bar, then to convert x bar into a z-score, we would take x bar minus the mean of the x bar values divided by the standard deviation of the x bar values. The only difference here is we're labeling this as d bar because they're coming from the differences in the matched pairs. It's the same thing, right? D bar minus the mean of the d bar values over the standard deviation of the t bar values. And if you remember from the central limit theorem, we knew that the standard deviation of the x bar values was the standard deviation of the x values divided by the square root of n. And that's exactly what happens here. This standard deviation here is simply the original standard deviation of the d values from here divided by the square root of n. Okay, so it's no different than that. We're just using a d instead of an x. Oops. Label that d bar, and then this would be sigma sub d divided by the square root of n, right? When you substitute for sigma sub d bar, which is the standard deviation down here. Okay, so here's the problem we run into. We don't know sigma sub d here because that would require us to know what the population looked like for all the d values, right? I mean, if I knew all the d values, I'd find mu sub d. I could just average them up. So, we don't know what these are because this requires us to know all the information from the population, which we don't. So we don't know sigma sub d. And if you don't know sigma sub d, the best thing to do is to substitute S sub d in for it. Okay, and that's what's happening down here. So you see you have d bar minus mu sub d bar over, if we plug in sigma sub d bar, which is sigma sub d divided by the square root of n, this would be a z-score. But we don't know this right here, right? We don't know what this is. We don't know sigma sub d. So in place of that, we substitute S sub d. But when we plug S sub d in for sigma sub d, that's where we get a t distribution. So that's where that t distribution is coming from. Now this is going to be our test statistic right here. So now we can convert any d bar value that we get over here into a t-score over here. Okay, so that's going to be our test statistic. All right, now going back to the traditional method that we were talking about. First thing you want to do when you do the traditional method is to find those critical values. So this is going to be a right-tailed test. Because remember, this points towards the right, so that means you have a right-tailed test. Eventually, these are going to be converted into t-scores. We know the t-scores are bell-shaped because of the d-bar values will be bell-shaped either because you're sampling more than 30 or because the original d values are bell-shaped from here. And in this problem, we're assuming that these are bell-shaped. So we're assuming this is true here, which gets us, the d-bar values will then be bell-shaped here, And then when you convert them to t-scores, they'll remain bell-shaped. So ultimately, these t-scores are going to be bell-shaped. And so again, with the traditional method, what you do is you first find the critical values. So that comes from your alpha, your significance level. So we're testing at 0.01, and we have a right-tailed test. And so if you remember, that basically means you have this much area in the right tail. Now, of course, if this had been a left tail test and the arrow pointed this way, then it would be 0.01 in the left tail. And if this had been a two-tailed test, then you would divide this up evenly among your two tails, and you just say 0.01 divided by 2, which would be 0.005. Okay, but anyway, you have a right-tailed test, 0 points towards the right, with this much area in that tail, so 0.01. And then you find the t-value, the t-score, where this occurs. And obviously it's a positive number, right? By the way, the degree of freedom, if you remember, is still n minus 1. So less than the sample size. Okay, so let's look this up. In our case, the sample size is the number of matched pairs that you have. So again, we have 1, 2, 3, 4, 5, 6 matched pairs. So that's our sample size. So our degree of freedom would be 5, 1 less than the sample size. Okay, so I'm going to look this up on a T table. So we're testing at 0.01. So we have 0.01 in one tail, which is this column here, at 5 degrees of freedom. So that occurs when T is 3.365. Okay. So that's our critical value. Okay, now let's run the test. Okay, and remember, when you run a hypothesis test, the first thing you do is you assume that the null hypothesis is true. And when you run a hypothesis test, it's all based on the assumption that null hypothesis is true. And so in this case, we're going to assume that the mean difference from the population, right? So the mean of the population differences is 0. We're going to assume that. In other words, we're assuming that if you take up all the, if you average up all the d values here that you get from the entire population, right? After subtracting population 2 from population 1, right? The matched pair here. Once you find all these differences from the entire population, the assumption that we're making is that this ends up averaging to 0. Okay. Now let's see what happens. All right. So now we're going to find our test statistic. Which is simply, yeah, Natalie, do you have a question?
No, sorry.
Okay, I was just making sure. So then the test statistic comes from fact that you're converting these D bar values into corresponding t-scores, and this is how you convert them into t-scores, right? So it's, again, if you're going to convert a D bar value into a t-score, you would say D bar minus the mean of the D bar values over the standard deviation of the D bar values. But again, if you don't know, and of course, the standard deviation of the D bar values would be sigma sub D divided by the square root of n. But if you don't know sigma sub D, which we don't, you substitute the standard deviation from the sample in. So the standard deviation of the differences from the sample. And once you plug S sub D in for this, it becomes a T distribution instead of a Z distribution. Okay. Okay, so let's go ahead and find this. That's our test statistic. Okay, so we need the D bar values. Well, what is D bar? D bar is the average of the differences from the sample. So if you look at the sample here, there's 6 matched pairs in our sample. We're going to find the difference in each of the matched pairs, and those are going to be our 6 D values from our sample. So you can do this on the calculator if you want. I went ahead and did this. If you go to stat and then edit, and you just put in all the president's heights in L1 and all their opponent's heights in L2, I've written them as matched pairs. So just make sure that you've matched them up. So you see 182 is the president's height and 167 is their opponent height. In this particular election, right? That's why they're matched together. So just make sure you keep them matched. All right. So I just entered all these in. 184 matched with 179. And what we're going to do is we're going to take 182 and subtract off 167, right? We're going to do that for every matched pair. And the numbers that we get here are called D values, and there are going to be 6 of them. And that's going to be our sample differences, our sample of differences. So the easy way to do that is once you've entered them in, you could actually go to L1, L3 and type in, notice I've got the cursor here up at L3, and then you can type in a formula for how you want to calculate L3. And all I'm going to do is take L1 minus L2. And L1 is this button here. So L1 minus L2. And then when you press enter, it will go ahead and say L1 minus L2 for every matched pair. And these are your sample differences right here. And what bar is the average of these differences. So we're going to have to average those up. So you can do that on the calculator as well. Once you have this, the differences from your sample, then you can go to stat and then go to calc and just use one variable statistics. Press enter. We do have to choose the correct column. So why is it not asking? So your calculator, newer calculators should ask this. Mine's not doing that for some reason. When you go to one variable statistics, it should ask you which column you're going to use to find that. So this is averaging up L1, I think. Okay, which is a little annoying for me because I have to redo all this. So I'm just going to do this. So what I'm going to do is put president's height into L2. So I just put these numbers into L2, and then I'm going to go over to L3, and I'm going to put their opponent's height in L3. And that's just because my calculator won't let me pick L3 for the differences. So let me type in opponent's height into L3, which would be 167. 179, 180, 176, 193, and then 175. And then I'm going to go to L1. So look, all I've done here is I put the president's height into L2 and I put their opponent's height into L3. And then I'm going to go to L1 and then type in L2 minus L3. So now the differences are in L1. Okay. And for my calculator, I guess I have to have them in L1. If you have a newer calculator, you can select, when you do one variable statistics, you can select which column you're going to do the one variable statistics on. Apparently, I can't do this on the older calculator. So do it this way if your calculator is like mine. Just make sure L1 has your differences in it. Okay. So now when you go to stat calculate, you hit one variable statistics, it's giving you, so this is the sample mean, which we're calling D bar, but they call it X bar. Average difference is 3.8 from that. This is the average from L1 now, right? My calculator always does L1, I guess. There's no way to change it. So that's your D bar, average of the differences from your sample. And then this S sub X is your sample standard deviation. So it's about 10.0, right? Remember, S stands for sample standard deviation. So those are the two numbers that we need in our formula. So let me write those down. So D bar is 3.833333. Now, mu sub D bar, you remember from the central limit theorem, mean of the D bar values is the same as the mean of the, we called them X bar values. The mean of the X bar values was the same as the mean of the X values. So the mean of the D bar values is the same as the mean of the D values. So that goes back to the mean of the D bar values, right? This right here, the same as the mean of the original D values here. That came from the central limit theorem. Mean didn't change, right? When you started looking at the D bar values, the mean did not change. So anyway, going back to that, we're assuming that this mean here is 0, right? That's something that we're making when we run the hypothesis test. All right, S sub D is about 10, 10.0 divided by the square root of the sample size, square root of 6. Now, what's happening here is mu sub D is really 0, right? So if this is really 0 here, right? The mean difference, the mean of the populations of differences, these numbers here, right? This is really 0. This averages to 0. When you sample 6 matched pairs and find the difference in those matched pairs, which we did in the calculator, you would expect the average of these 6 numbers that you 6 matched pairs. You'd expect that the average of the differences there would be close to 0, right? Because you're drawing from a population where average is just 0 for the entire population. And you're trying to determine if that's happening. We're averaging up to 3.83. Now, the question is, how close is that to zero? I mean, the absolute difference between this and zero is 3.83. That's how far away it is. It doesn't mean much to us. We want to know how many standard deviations this is away from zero. And that's what the bottom number is. The bottom number is what a standard deviation is. So if you look at it, a standard deviation in this particular case is 10 divided by the square root of 6. So every 4.08 units constitutes a standard deviation. That's what the bottom number is. This is what a standard deviation is. So if you're 3.83 away and you divide that by what a standard deviation is, we're not even one standard deviation away. We're about 0.38 standard deviations away. That's how far 3.83 is in terms of a standard deviation. And that's what the test statistic is telling us. Okay, so D bar is 3.83, which is 3.83 away from what we expected it to be, because the mean of the differences from the population we're assuming would have been zero. So if you're really drawing from a population where the mean of the differences is zero, then you would expect to get something close to zero for your sample mean. And we didn't. We got something like 3.83. How far apart is that from zero? It's 0.938 standard deviations away from zero. That's what this tells us. And so the question is that too far away to believe that mu sub d could reasonably be zero? And when you look at it, we already set up the boundary. We said anything more than 3.365 standard deviations away was too far away to believe. So in this case, we're going to fail to reject null hypothesis because the test statistic landed right here. So it did not land in the critical region, right? So if the test statistic does not land in the critical region, then you fail to reject null. Again, the reason you're failing to reject null is because the D bar value, sample mean, is only 0.938 away from our assumption about what the population mean is, which is zero. It's only 0.938 standard deviations away. Would have had to have been more than 3.365 standard deviations away for us to then say, I don't believe my assumption is correct, mu sub d is zero. So that's why we're failing to reject this. It seems reasonable that mu sub d could be zero. If mu sub d were really zero, and I sample 6 matched pairs and find the difference between them and average them, find the average of those differences, get bar, I got 3.83. It's not crazy, right? It's not outlandish to believe that that could have happened because 3.83 is only 0.938 standard deviations away from zero, which is not that far, not far enough. Anything more than 3.365 is considered too far. So this seems possible, reasonably could have happened. So we fail to reject the null hypothesis. Could be that mu sub d is zero. It seems like it could be a possibility here. And then what does that say about the claim? So if you're failing to reject the null, then you're not able to support the alternative, and the alternative is the claim. So there's not sufficient evidence to support the claim. Okay, so that's what happens in this case. Now look, in order for me to have supported your claim, what would have had to have happened? You know, let's say D bar turned out to be 15. So the average difference in the sample was 15 units, right? And have 50, the difference between 15 and our assumption about mean difference from the population being 0, it's 15, absolute difference is 15 units away. Then again, you would have to convert this into a number of standard deviations. So you'd say 15 divided by that, what a standard deviation is. So you'd say 15 divided by 4.08, because that's what a standard deviation is, every 4.08. That would have been 3.67 standard deviations away, right? So if D bar had been 15, I'm sorry, this is a T, this is D bar, instead of 3.83, right, which is what we got. But if, let's say, D bar had been 15, average differences from the sample. If that had been 15, then that would have converted into 3.67 standard deviations. That's how far away it is. 15 is from 0. That is past our boundary. Then you would reject them all because you landed in the critical region. Test statistic, right, would have. Then you're saying, I don't believe it. I don't believe mu sub d is 0. The reason I don't believe it's 0, which, remember, this is the assumption that we make when we run the test, but we're testing that assumption. The reason I don't believe it is because 15, my average from the sample, is so far away from what it should have been, which was 0, right? If this was true, right? I mean, if this is 0, then my D bar should be something close to 0. 15 is not close to 0. It's 3.67 standard deviations away. Once you're past 3.365, that's when you say, I don't believe it. Okay, so then reject this null hypothesis, and that means there's evidence to support the claim now. So technically, you're rejecting the null, which means there's evidence to support the alternative, but then the alternative happens to be the claim in this case. So if you're supporting the alternative, you're supporting the claim in this particular case. And so then that's when you would have evidence to support the claim. Okay, so then let me just do the p-value method. We'll get the same result. So remember, when you do the p-value method, don't find the critical values first. Again, we're still doing, testing at 0.01. That's the same thing, significance level. But when you do the traditional method, you don't find the critical value, right? You don't bother finding the t-score that goes with this, which happened to be 3.36 something, whatever it was. You don't find that critical value. You don't find that boundary. All you do is you run the test, assume the null hypothesis is true again, that mu sub d is 0, find the test statistic based on that assumption. You're determining how far away d bar is from this assumption, and it turns out to be the same thing, right? 0.938 standard deviations away, which puts you right here. So you locate the test statistic on your little distribution picture, and then either find the area to the left of this test statistic or to the right, and that's all determined by which way this arrow points. This is a right-tailed test, so you're going to find the area to the right of the test statistic. So we need to find out what this area is, and whatever that area is the p-value. And since this is a t-distribution, you can do that using tcdf. So go to your distribution list, scroll down to tcdf, and you're just going to find the area between the two t-scores here, 0.938 and infinity, right? this goes to infinity. So anyway, let's find it. 0.938 to infinity. So we're finding the area. We're finding the area between those two t-scores. Then the degree of freedom again is 5. Got to put that in at 5 degrees of freedom. So the area in there is about 0.196. And then you compare the p-value directly to the significance level alpha. And so here you can see the p-value is greater than alpha. And whenever that happens, you fail to reject the null hypothesis. So if the p-value is greater than or equal to alpha, then you fail to reject the null. Okay, and it's the same thing we had before. So if you fail to reject the null, you're saying again that this assumption that we made about mu sub d being 0 seems plausible. Therefore, you can't support the alternative hypothesis, which happens to be the claim. So again, there's not sufficient evidence to support the claim, just like we had before. So it's no different. The result is no different than what we had when we did it using the traditional method. Now, one other thing I want to mention about this p-value method, which may help you understand what's going on a little bit, is p-value is really a probability because it's an area, and area is the same as probability. So what is it the probability of? It's the probability of getting this test statistic or something bigger than this test statistic. If mu sub d is 0. So if mu sub d is 0, there is a chance that we would get d bar value to be 3.83. Remember, the d bar value of 3.83 turned into, this is 0.938 standard deviations away from our assumption that this is 0. If d bar had been something like 3.9, then that would have had a t-score, like number of standard deviations. If you write that as a t-score, then it would land somewhere in here, right? A little bit more than 0.938, right? Because if this is 3.9, then this is going to go up a little bit, way above 1, like 1 point something. I'm just making it up. It's going to be a little bit larger than not 0.938 because it's further away. So all these little test statistics in here above 0.938, all these t-scores, they're t-scores that come from d bar values that are above 3.83. And so what's this area represent? It's the probability that your test statistic would be 0.938 or bigger than 0.938. That's what this represents, right? It's the probability of being 0.938 or larger under the assumption that mu sub d is 0. Okay, so one last stab at what this p-value says as probability. If mu sub d is 0, if it really is 0, like we're assuming it is, then the p-value is the probability of getting a d bar value, a sample mean that is has a standard deviation of 0.938 or larger away from 0. Probability of that happening happens about 19.6% of the time, right? Mu sub d is 0. I get 3.83. How likely is this to have happened? this happens, or worse, right? Or larger. If this is 0, what's the chance of getting a D-bar value of 3.83 or higher? Happens 19.6% of the time. That's what this tells us. And we already decided up front that anything less than 1% is highly unusual to us. That's what this alpha represents. And our p-value was more than that, and that's why we failed to reject the null. It happens 20% of the time, which is often enough to believe that this is plausible, and u sub d is 0. If it had been less than 1% of the time, though, the probability, that's when we would reject the null. So if this p-value had been like 0.001, so it happens 1 in 1,000 times, mu sub d is 0, and you end up getting a d-bar value that happens, a d-bar value or greater happens 1 in 1,000 times, and that's less than 1% of the time. That's when we say, okay, I don't believe this is 0. So I got something that happens 1 out of 1,000 times. That's 0, and that's why you reject null in that case. Okay, you can also do this on the calculator, so let me show you real quick. Effectively, what we've done is once you've done this, where you start with two populations, population 1 and population 2, because you have matched pairs. Once you find the differences between the two matched pairs and you reduce it down to a bunch of these differences here, or your population differences, once you've done that, effectively you've reduced this to a problem that has one population in it. It's a population of differences. And we did this in chapter 8, I think it was 8.3, where we looked at claims about one population mean. So we've reduced it to a claim about one population mean. Claim is about this population mean right here, single population mean mu sub d. So it's essentially what we did in 8.3 now. We're making a claim about one population mean, right? Which is what 8.3 was about. So once you've found the differences between the two matched pairs and created a single population, the population of differences, you've effectively reduced this problem from a two population problem to a single population problem, where you're making a claim about a mean in that population, mean of the differences. So because of that, you can actually go to stat tests and then scroll down to the very test that we used in 8.3 for claims about single population means. It's either a z-test or a t-test. It's a z-test if you know sigma, in this case, sigma sub d. So if you happen to know sigma sub d here, it would be a z-test. That's not very realistic, as we mentioned before. We don't know sigma sub d, so we have to substitute S sub d, the sample mean, sample standard deviation, and that's why it becomes a t-distribution, so it's a t-test in those cases. And this is the realistic case. So then you have to select data or stats. We've already put the data into the L1 and L2, and u sub 0, you remember, that's how they're labeling the null hypothesis is telling us about mu. So they label this as mu sub 0 because it matches the sub 0 for the null hypothesis. So what is mu sub 0 from the null hypothesis equal to? Well, it's equal to 0. That's all that means. So for us, mu sub 0 is 0. The list that we're drawing our data from is L1 because that's the differences, right? I put the differences in L1. Now, if you have it in a different list, make sure you change it. Originally, I had it in L3. So if it was in L3, change it to L3, right? But I went ahead and put it into L1. Keep the frequency at 1, don't change that. And this is your alternative hypothesis, which is that don't label it as mu sub d. They don't know you're talking about population of differences. Call this mu sub 0. Mu sub 0 is 0, right? From here. Then they just call this mu. So when you look at the calculator, what's alternative hypothesis? It's either mu is not mu sub 0 or less than mu sub 0 or greater than mu sub 0. And for us, it's greater than mu sub 0. In other words, mu is greater than 0. Mu sub 0 is 0. And you calculate that. All right, so there's your test statistic, 0.936. Same thing we got before. And there's your p-value, 0.196. The way it gives you the d-bar value, 0.83, that's the average from the sample. And then your sample standard deviation is 10.0, right? We had before. So anyway, that's how you can do that problem. And notice for part A, that's what we had for our null and alternative. If you round it to 2 decimals, it's 0.94. There's your test statistic, and there's your p-value, 0.96. And they're doing the p-value method, I guess. Remember, the p-value is greater than alpha, the significance level. You fail to reject the null hypothesis. And we said that that means there's not sufficient evidence to support the claim. So they're getting the same result. Okay, last thing, part B. You may remember this. You can also test claims by looking at confidence intervals. Now, typically we don't do this, but sometimes you can. If you're if you're testing a claim, it's probably best to do it using a hypothesis test like we did in part A. But if you want, you can look at a confidence interval to sort of test someone's hypothesis as well. And that's what part B is about. What they want us to do is to come up with a confidence interval for mu sub d. So remember, we don't know what mu sub d is. I mean, one of the things we could do is try to estimate what it is as a single number. And if we did that, the best thing to use would be the sample mean bar. And for us, d bar was 3.83. Remember, this was our average from the sample, right? So if someone asks you what your best guess as to what this number is, right? Going back to mu sub d, right? If someone says, hey, what do you think this averages to here, right? All these d's, what do you think they average to as a single number, a point estimate, would say d bar, sample mean, 3.83. So that's your best point estimate. But what we want to do is come up with a confidence interval. Remember, point estimates aren't as good as confidence intervals. So they want us to come up with a confidence interval to test this claim. Now, the first question that we have to resolve is what level of confidence, like what percentage should we work with for a confidence interval? And that goes back to part A. We did a hypothesis test with alpha equal to 0.01. Let me double check that. I think that's what it was, right? Alpha was 0.1. So in part A, notice, right, we were running a hypothesis test to test the claim at a significance level of 0.01. And it was a right-tailed test, right? This was right-tailed of this. So picture that we have is, we have a T distribution, and when we did the critical value, we had, a right tail with this much area in the right tail. That's the level of the significance level. And this turned out to be some T-score, 3 point something. Okay, so that's what it looked like as a hypothesis test. So part B, we're going to use a confidence interval to test the claim instead of a hypothesis test. Here's the issue is, what level of confidence do I want for my confidence interval to test this? And this can get a little confusing, but look, a confidence interval has two tails with the same amount of area, and then whatever's left in the middle is the level of confidence for your confidence interval. So if from part A, you have a right tail with 0.01 in it. If you want to convert that into a confidence interval, then you have to have another tail on the left side with the same amount of area. So if you want to convert this into a confidence interval, you would have to have another tail on the left side with the same amount of area. So you would have to have a left tail with an area of 0.01, and that would leave you with the middle area being 0.98. And that means you have to have a 98% confidence interval. So a hypothesis test looks like this from part A, where you have 0.01 in the right tail, converts to a confidence interval of 98%. So that's what we're going to find for part B, is a 98% confidence interval for mu. Or mu sub d. Okay, so mu sub d is trapped between d bar plus the margin of error and then d bar minus the margin of error. Remember, d bar is our point estimate, and you take your point estimate and you add the margin of error to get the high number and subtract the margin of error to get the low number, and that's your confidence interval for mu sub d. The only question we have is, how do you find the margin of error in this case? And it's no different than what we did before. When we did this before, we labeled this a little different. But instead of mu sub d, we called it mu, but we found a confidence interval for a single population mean by taking the sample mean, x bar, and adding the margin of error and subtracting the margin of error. The only difference here is we're calling these bar values, and we're calling this mu sub d. And the margin of error in that case was a t-score times the standard deviation over the square root of the sample size. So up here, it's the same sort of thing. It's a t-score. Now, standard deviation here we label as S sub d. Standard deviation in the d values from our sample divided by the square root of n. So let's just find it. Now remember, this is coming from, I guess this was probably 7.2, right? When we did confidence intervals for a single population mean. And this is now 8 or 9.3. So anyway, let's find it. So this t-score is t-score here, right? Which is exactly the same thing that we found up here. If you go back and find it again, what you would do is go to the table. We did this before, but you go 0.01, 0.01 and one tail, which is 0.02 and two tails, same thing. And you go down to 5 degrees of freedom, and it's the same number we had before, 3.365. It's no different than our critical value from before. It's the same number on here. That's what this refers to. That's, the t-score with this much area to the right of it. So 3.365 times S sub D, which was 10.0, divided by the square root of the sample size, which was 6. And there's our margin of error. Okay, so the margin of error is about 13.74. I'm just going to round that off. And then, of course, what you do from there is take your point estimate, which I believe was, let me just double check it, 3.83 or something like that. Yes, 3.83 was our bar value. So you take 3.83, you add the margin of error, the high number, then you take 3.83 and minus the margin of error to get the low number. Okay. And of course, you could put this in the calculator if you wanted to figure out what those are, but you could also just do this. Go to stat, tests. Now, instead of t-test, go to t-interval. You're just doing a confidence interval for one population mean where, you remember we had z-interval or t-interval for these possibilities. Whether if you knew sigma, it would be a z-interval. But if you don't know sigma, then it's a t-interval. And the data, I've already got the data, so I can do that, or I can do the stats. If you do the stats, this is your D bar, this is your F sub D, it's 6, and you do a confidence level of 0.98. And this is what you get for the low number, this is what you get for the high number. You could type those into your calculator, you should get the same answer. So the high number is 17.609, and the low number is negative 9.943. That's what you should get when you type those in, right? Doing it by hand. And also, by the way, if you go back and, like I said, if you go to stat tests and do the t-interval, of course, if you've already put the data in, you can pick data, then just pick whatever list you put the D values in. I put them in L1, and then make sure you have the confidence level at the correct number, 0.98, and get the same answer. Now it's just taking it from a 1 instead of taking the summary statistics. Okay, so what does this mean? We're 98% confident that the real mu sub D is somewhere between this number and this number, based upon the sample data that we got, which is a pretty high level of confidence, right? I mean, we don't know what this number is, but based upon the sample data that we got, we're 98% confident that it's between these two numbers. And so now we're going to test your hypothesis based upon that confidence interval. Your hypothesis was that mu sub D was greater than 0, right? That was your claim, which happened to be the alternative. So then I can look at this and decide which of these hypotheses seems more reasonable. So are we going to, you do it the same way you did before. You either reject the null or you fail to reject null. That's the approach that you need to take here. So you do that first. You don't decide the claim first. You decide whether you're going to reject the null or fail to reject the null. Just using the confidence interval to do that instead of the hypothesis test. So when you look at this, you have to decide whether you believe that mu sub d being equal to 0 is a reasonable possibility. Is it plausible? And when you look at the confidence interval, I think it's a reasonable possibility because we're 98% sure that it's between negative 9.9 and 17.6. 0 happens to be in that interval. So I'm 98% confident that it's somewhere in there. It seems reasonable that this could be mu sub d. So I cannot reject this possibility. So I'm failing to reject the null hypothesis. Because mu sub d being 0, 0 is in this confidence interval. So I can't reject the null, and that leads to the same conclusion. Failing to reject the null means you can't support the claim, the alternative, which means you can't support the claim. So you fail to support the claim. Or not enough evidence to support the claim. Okay, that would be the same conclusion that we had when we did the hypothesis test. Now look, one last thing and then I'll let you go. If suppose the confidence interval was negative 15 up to negative 2, and we're 98% confident that mu sub d is somewhere in here, then you ask me whether I think this is a reasonable assumption. Mu sub d is 0, right? Because that's you're assuming the null hypothesis is true. Is that reasonable based upon confidence interval? And I would say no, because I'm 98% confident that mu sub d is somewhere in here, and 0 is not in there. 0 is above negative 2. It's here on the number line, right? So it doesn't look like mu sub d is 0, right? I'm 98% confident that it's between negative 15 and negative 2, which means it probably isn't 0. And that's when I would reject your null hypothesis. I don't believe this is 0 because of this. And then if you reject the null hypothesis, the same sort of stuff happens. Now support the alternative, which is supporting the claim. So then there would be evidence to support the claim in that case. Anyway, that's how you would do it using a confidence interval instead of a hypothesis test. So if you notice at the very bottom, this is your confidence interval. They rounded it to 1 decimal, but it goes from negative 9.9 up to 17.6. And then the conclusion that they make is that since the confidence interval does contain 0, right, mu sub d equal to 0, is that reasonable? Yes, because it's in the confidence interval. You can't reject the null hypothesis. So you have a failure to reject the null, which is exactly what happened up here. See, you failed to reject the null hypothesis, and there's not sufficient evidence to support the claim. They didn't say that down here, but once you fail to reject the null hypothesis, that would be your conclusion about the claim. Okay. So again, I went a little bit over time here, but I wanted to get through all that. Anybody have any questions about this before we did it?
No.
Okay, you're okay with this? Okay. Don't forget, I guess the next test next week will be over chapters 9, 10, and 11. We're going to finish tomorrow. We'll finish chapter 9, and then there's 2 sections in chapter 10, which we'll finish, I guess, on Thursday and Friday. And then next Monday, we'll start talking about the 1 section in 11. So we'll be done by next Monday. And then you'll have to take the test before, I guess, Thursday, because that's the last day of class, and then the final also. So next week might be a little bit busy because you'll have to take the fourth test and then the final. All right, so we'll leave it there. If you have any questions, just let me know. Email me or whatever, and I'll help you out, okay? Okay, we'll end it there. Have a good
Okay,
day, and I'll
thank
see you
you.
tomorrow. Okay, bye-bye.
Bye.